Hi dear students, today we have come with a new video of class 10, that is refraction of light through plane surface. Okay, so first I have to discuss about the whole title what we have written. So first we have to come with refraction. What is it? What is refraction? See, it is a property of light which is shown. Initially, we have learned in class 9, that is reflection, that when a light ray travels from one medium and incident on a shining surface, then it reflects back to the previous medium. Okay, refraction, it is also one property just like reflection. Okay, but what is it? We know in our around we have seen many more transparent material. Okay, though the transparency of different materials are not same. Okay, so if we assume that a light ray coming from one medium and just passing or just moving to another medium, then what happens? That time we have seen that whenever the light comes from one medium and travels to another medium, the light ray bends. It is a property that is shown by light. Okay, similarly we have shown to you, assume it is one medium, we have given a name medium 1, and it is another medium, that is medium 2. So this one, if I have given a name AB, this AB is the separation between the two mediums. When the light ray coming from medium 1 and just incident the separation between two medium, then we have seen the light ray bends when it travels to another medium. Okay, it bends, its path is bent. That property is known as refraction. So if I tell it together, that when the light ray travels from one medium to another medium, that time the path of the light ray bends from the intersection, from the junction of the two medium. That is known as refraction. Okay, so whenever the story has come in front of you, immediately after the thing has come, what is the cause of it? What is the cause? The general cause of this refraction is that we all know that when a light travels in a medium, it will pass with a speed. The speed of light is maximum in free medium or the vacuum, or you can say in air also. It is 3 into 10 to the power 8 meter per second. But when it travels from one transparent medium to another transparent medium, then the speed of the light gets changed. Okay, so when the speed is changed, then the path of the light is also changed. I am giving you a idea. Assume you are going by a bicycle with speed. The road is totally clear. Suddenly, whenever you are come to a crossing, that time you feel there is some traffics are there. So it is not possible that in which speed you are coming, you can go by that way with same speed. It is not possible. Then you will bend your path and you just find on which direction there is less traffic. You just want to go by that way. Okay, and that your path bends, and that is the cause of refraction we have seen. I've given you an example. You feel that whenever we have looking to an object, when no obstacle in front of us, then it is pretty clear for us. But assume if I see the same thing by any of the transparent media, just like if I see it by our glass, okay, the specs we have here, that time the visibility, it is little changed. If I assume we are taking a glass which is having a different color, then the visibility changes a lot. if I have seen the same object through a glass slab, then its position, its apparent position, that is changed. If I see it through the water, then the apparent position of the object we have seen earlier, it is changed. The reason is that the path through which light ray travels, the path is bent when it travels from one medium to another medium when it comes obliquely with an angle. Okay, that is the refraction. So whenever we are talking about the cause, the one and only cause that is coming, that is speed of light changes from one medium to another medium. Okay, now based on the speed of light, we can justify, we can identify the transparency of a medium with a term, with an idea, with a concept, and that is known as optical density. Now we have to see what is optical density. Let's see it. Okay, so our next target is to learn about optical density. What is it? What it tells to us? See, we have seen in some medium the speed of the light which is more, but in some medium is there where the speed of the light is less. Assume in the refraction we have seen the light ray comes from one medium. Assume here the speed of the light is v1 and it goes to another medium. Here the speed of the light is v2, and if we see here the speed of the light v1, it is greater than v2. So we can say that when the light ray travels from medium 1 to medium 2, the speed of the light decreases because initially the speed is more. When it comes to another medium, the speed decreases. So that's why if it is happened, then the second medium is known as optically denser medium than the previous medium. The second medium is known as optically denser medium than the previous medium. That means the first medium. So the first medium is known as rarer medium and the second medium is known as denser medium. Now don't mix it with the concept of density with optical density. I'm clearing this thing previously that optical density and density, these two things are not same. Density means mass per unit volume, but optical density means it is a property by which we can say how much the speed changes when it travels from one medium to another medium. Here we have seen the light comes from first medium to second medium, the speed decreases. So optically the second medium is denser than the first medium. If the opposite thing is happened, assume the light ray comes from the first medium and it goes to the second medium. It is medium 1, it is medium 2. Here the speed is v1 and here the speed is v2. In this case, if you see that v1 is less than v2, and by that we can say that medium 2 is optically rarer than the first medium. Medium 2 is optically rarer means less denser. Rarer means less denser than the first. So first medium should be known as it is a denser medium and second medium should be known as a rarer medium. That is a concept of optical density. So optical density is not a thing which is just correlated with the general density concept we have seen. So optical density depends on the speed of light. If the speed of light is more in a medium, then the medium should be known as less optically denser, and if the speed of light is less through a medium, then the medium is known as more optically denser. Okay, I think this concept is clearer for you. Now coming to the case of refraction, what happened when the light ray comes from rarer to denser medium? Though the diagram I have already drawn, but here I will draw it again for you. If it is optically rarer medium, that is medium number 1, and it is optically denser medium, that is medium number 2, when it comes, we have seen that light ray, it just bends towards the normal. It is normal, we all know from the reflection, but for the case of reflection we have seen the normal is only on upper side, but here as it comes to the second medium, so that's why we have taken downward also, and it is the separation between the two medium. And in this case we have seen the light ray, it should go in this path if there is no second medium, but the light ray bends towards the normal. Okay, so when a light ray comes from rarer medium to denser medium, it just bends towards the normal. And oppositely, when the light ray comes from denser medium to rarer medium, so assume it is denser medium and it is medium 2 and it is rarer medium. If the light travels, okay, that time we have seen the light bends away from the normal, because if there is no medium, the medium is same with the medium 2, it will go by this path, but we have seen the light bends up to this position. Here we have to mention the angles also. The angle which is made by the incident ray, if I have given the name, if it is P, if it is Q and it is R, so PQ is the incident ray and it is making an angle with the normal. So this is as per the reflection, it is angle of incidence. And if I am talking about this QR, it is refracted ray. Okay, as this ray is shown due to refraction, so it is known as refracted ray, and this angle is known as angle of refraction, that is R. Here also the light ray, it is coming from here. So this PQ, it is making an angle with the normal, that is angle of incidence, and this one, it is angle of refraction. Okay, so in first case, if the light ray travels from rarer to denser, so that case angle of incidence is greater than angle of refraction. But in opposite case, when the light ray travels from denser to rarer, then angle of incidence is less than angle of refraction. So these are the common things we have seen in case of refraction. Okay. Now we are coming to the next part, that is partial refraction and diffraction from a plane or through a plane. Partial reflection and refraction through a plane. What is it? Now, when light ray travels from one medium and it is incident, the separation between the two different mediums with an angle. Okay, so when the light ray travels just this way and incident here at the point Q, then we all know that some light travels through the another medium. If it is a rarer and it is a denser medium, it will just bend towards the normal. But some portion of light, it can be reflected from the surface, the separation between the two mediums, that is AB. So if it is angle of incidence I, this is angle of refraction R, and this one is angle of reflection R dash. We can denote it by R dash. So it is PQR and this is S. So together refraction and reflection is possible. I am just making you remember whenever you have learned reflection in class 9, that time we have learned that in the case of reflection, some amount of light it is absorbed by the surface. Okay, so what the light is absorbed, that is basically passing through the medium as a form of refraction. So absorption is nothing but the refraction we have seen. Okay, so that is partial reflection and refraction. Same thing it will happen if the light ray travels from denser to rarer medium. So that diagram I have not shown here. You all know that what will happen because you have already done it earlier. Now the question has come that whenever we are talking about the refraction or this thing, on which thing the refraction depends and when the light ray will be gone or move through one medium to another medium without any deviation. Okay, so for that case we have to see it. If the light ray travels through an angle with the normal, then the light ray bends if it is rarer and it is denser. It is very much clear that the light ray should gone to this path, but due to the presence of another medium, the light ray bends. Okay, so you see there is an angle of separation that through which the light should go and where the light exactly gone. Okay, so if I given the name P, Q, R and it is S, so the light in generally gone to PQS path if there is no another medium, but due to the presence of another medium, the light ray just bends to QR path. So in that case, this angle is known as angle of deviation because it is deviated from its own path. But if I am just changing the angle of incidence, assume I am just decreasing the angle of incidence and make the angle of incidence 0. So angle of incidence 0 means it is just coming through the normal. The angle, the incident ray, it is just coming through the normal. So that means angle of incidence is 0 degree. In this case, we will see a very interesting thing that the light ray will just pass to another medium. If it is rarer, if it is denser, so it will pass from rarer to denser without being deviated in any direction. The same thing will happen if you make the light incident from the denser medium also with an angle of incidence 0 degree. So it is clear if the angle of incidence is 0 degree, so angle of refraction is also 0 degree. It is the only case when the light ray will travel from one medium to another medium without being deviated. Okay. Now will come the common thing, okay, that we have learned for the case of reflection and we have to learn for the case of refraction also. So laws of refraction. What are the laws of refraction? So just like reflection, there are also two laws of refraction. First, before writing the laws, we have to draw the diagram again. Several times we have drawn the diagram, and one thing you have to keep in mind, we have to mention the separation, we have to mention the angle as well as the direction of light, which is very important, and the incident and refracted ray. Okay, you can give the name whatever your choice, but you have to give the name. Now, the first law. What is the first law? The first law tells us that is exactly the second law of reflection. That is incident ray, refracted ray and the normal on the point of incidence all are lying in a same plane. Incident ray PQ, refracted ray QR and the normal N dash at the point of incidence Q or are lying in a same plane. See, I have drawn the diagram in a plane of board. And the same thing is happened for the case of refraction also. That means if the light ray comes by this path, it will gone by this path. It is not like that. After coming here, it will gone like this way. It will not change the plane. The plane should be constant. That is the first law of refraction. Number two, which is very important. The number two is the sine of angle, the ratio of sine of angle of incidence to the angle to the sine of angle of refraction is always constant for two constant mediums. What I have told? The ratio of sine of angle of incidence to the sine of angle of refraction is always constant for two constant medium. So if I am taking it is medium 1 and medium 2, angle of incidence is I. So sine of angle of incidence is sine I. 2, the angle of refraction, sine R. It is always constant. That means the ratio of sine I to sine R for two constant mediums are always constant. That is the second law of refraction. Okay. Now, what is that constant? That we have to justify in the next part, that is refractive index. Just now we have discussed about optical density. But the problem is that whenever we have to define or we have to justify or we have to show a quantity, we have to find and we have to measure it. What should be the measurement of optical density? So to measure the optical density, we have defined another constant quantity that is known as refractive index. What is it? Again, we have to come with the diagram. Okay, we have to come with the diagram. That is angle of incidence I, angle of refraction R. It is AB, it is N dash, P, Q, R. Okay. What is refractive index? As per, we are just doing a continuation from the laws of refraction part 2, and there we have seen the sine I upon sine R. It is a constant for two constant medium. This constant is known as refractive index of one medium with respect to the other medium. That means if the light travels from medium 1 and it goes to medium 2, then this sine I by sine R, it signifies, it is the refractive index which is denoted by mu. This U-shaped thing, it is known as mu. It is written like this way. One side is little longer and second side is shorter. So it is written as mu 2 1. What is justified? It justifies that it is refractive index of medium 2 with respect to medium 1. That means from which medium light ray comes or from which medium the incident light comes, we have to define the refractive index with respect to that medium. Okay, so sin I by sin r equals to 1 mu 2, or it can be written as mu 2 by mu 1. That is refractive index of second medium with respect to first medium. That is. Now you might be thinking, sir, whenever we have written mu 2 or mu 1, that is also a refractive index, and it is also measured by the respect of another medium. So what is that medium? In generally, whenever you have to mention any refractive index like mu 2 or mu 1, this is measured with respect to vacuum. It means if it is 1, it means it is refractive index of medium 1 with respect to vacuum. It is refractive index of mu 2 with respect to vacuum. So as we have written it, mu 2 by mu v, we have taken that refractive index of vacuum is 1. Refractive index of vacuum is 1. So that's why it has come mu 2 and mu 1. Okay, so that's why we have written directly mu 2 or mu 1. But if the light ray comes from 1 to 2, so it is written as 1 mu 2 mu. Okay, mu 2 by mu 1. That is refractive index of medium 2 with respect to 1. If the light ray comes from air to glass, okay, so we can mention the refractive index sin I by sin R. It is equals to refractive index of glass with respect to air, mu g by mu a, or you can write a mu g. Okay, because the light ray comes from air and it goes to glass, so here this answer will come. But if the opposite thing is happened, assume the light ray comes from the glass and it goes to air. It is coming from glass with an angle of incidence I, and it is goes to air with an angle of refraction R. It is air and it is glass. Okay, so what will happen in this case? So in this case also we have to find sin I by sin R, but the refractive index from which medium the light ray incidence, with respect to that medium the refractive index is measured. So it is refractive index of air with respect to glass, or it can be written as G mu A. Okay, G mu A. So from this two we can write that A mu G, it is equals to 1 by G mu A, because these are the reciprocals. It is mu G by mu A and it is mu A by mu G. So we can conclude A mu G equals to 1 by G mu A. Clear? Okay, see that portion properly. A mu G equals to G mu A. So if we have written that A mu G equals to 3 by 2, okay, then G mu A, that should be 1 by 3 by 2, and that is 2 by 3, exactly reciprocal. Okay, so the idea of refractive index, that depends on different medium, from which medium to which medium the light comes. Depending on that we can able to find the refractive index. Okay, now we'll go for the next part of refractive index, that is the relation of refractive index with speed of light, because the all story we have seen, that is due to the speed of light only. Relation of refractive index with speed of So what it tells to us, let's see. Assume if a light ray comes from the vacuum and entered to a medium. So we know the vacuum, it should be the rarer medium always. Okay, and when it enters on another medium, that should be the denser medium. So it is angle of incidence I, angle of refraction R. This is the separation AB, PQR. Okay, this is the light ray. So when a light ray comes from vacuum, then the refractive index is related with the speed of light, just like this way. The refractive index of the medium, assume the medium we can take, it is taken by M. Okay, and it is coming from V. So we can write refractive index of the medium with respect to vacuum, and it is written as speed of light in vacuum by speed of light in a medium. So in generally, the speed of light in vacuum, we denote it by C, and speed of light in the medium, assume that is V. Okay, and that's why the refractive index will be C by V. See one thing here, that C, that is speed of light, and V, that is the speed of light in that medium, both are speed of light. So the ratio, as it is refractive index, so it is unitless quantity. That thing you have to remember, that refractive index, it is a unitless quantity. Let's see some numericals and how we can able to calculate the refractive index. We all know the speed of light in vacuum equals to 3 into 10 to the power 8 meter per second. And the speed of light in glass, we have denoted by Vz. Speed of light in glass, that is 2 into 10 to the power 8 meter per second. So if a light ray comes from vacuum to glass, then what will be the refractive index of the glass with respect to vacuum? So it is denoted by mu g v. V mu g, that means refractive index of glass with respect to vacuum, that is 3 into 10 to the power 8 by 2 into 10 to the power 8. 10 to the power 8 will be cancelled out, 3 by 2, that means 1.5. Okay, so that should be the refractive index of glass with respect to vacuum. In the case of air also, we have taken the speed of light is 3 into 10 to the power 8. So you can write A mu g, that is also 1.5. Because what is the speed of light in vacuum? Same speed of light in case of air also. Okay. Now the question has come, if we are just taking the light is coming from vacuum, if it is not happen, if the light comes from one medium and it goes to another medium, so in that case how we can able to find the refractive index? It comes from one medium and goes to another medium. Simple thing, just like the light ray is coming from medium 1 and goes to medium 2. It is medium 1 and it is medium 2. It is coming with an angle I and going to an angle R. That is the path in generally it goes. But definitely medium 1 is rarer and medium 2 is denser. So it deviates towards the normal. It is P, Q, R and it is AB. It's a very common thing. Okay. And in this case, I want to find the refractive index. We know the refractive index, it should be mu 2 1, because the light ray comes from the medium 1, and that is mu 2 by mu 1. It is sin I by sin I. Then let's see one another thing, that what will be the speed of light in medium 1? Assume the speed of light is v1. In this medium 2, the speed of light is v2. Then what should be the relation? We know mu2 it is equals to c by v2. Just now we have seen mu2 means, actually whenever we have written mu2 or mu1, that refractive index is calculated with respect to vacuum. So it should be c by v2. If I am talking about mu1, it can be written as c by v1. Just now we have seen. So let's put the value here. That is 1 mu2, that can be written as c by v2 by c by v1. That is v1 by v2. That means speed of light in medium 1 by speed of light in medium 2. Okay, let's see an example. Assume the light ray is coming from glass to water. The light ray is coming from glass to water. Okay, I have to come here across. The light ray is coming from glass to water. Comparatively, if you see that glass is little denser than water. So when the light ray will come here, it will deviate away from the normal little bit because it is glass and it is water. So the speed, generally we know the glass is optically denser than water. What is the speed of light in glass? If we see, the speed of light in glass is 2 into 10 to the power 8 meter per second. Just now we have seen, that is Vg. What is the speed of light in water? So Vw, it is 2.25. So very little increase. Okay. So what will be the refractive index then? Then refractive index 1 mu2, because we have taken the medium 1, it is medium 2, or we can write it g mu w, refractive index of water with respect to glass, that should be equals to Vg by Vw, velocity of light in glass, because speed of light in medium 1. So here medium 1 is glass, because from there the light ray is coming, by speed of light in medium 2, that means speed of light in water. So let's put the values. So 2 into 10 to the power 8 by 2.25 into 10 to the power 8. It will be cancelled out. So 2 by 2.25. So 2 means it's 200 and 2.225. So let's divide it by 5 first. It is 40. It is 45. 5 8s are 5 9s are, I'm sorry. So it should be 8 by 9. That will be the answer. Okay. One thing you see, I just want to show you from here, that when the light comes from denser to rarer medium, then the refractive index, it is less than 1. When light ray comes from denser to rarer medium, the refractive index comes to less than 1. And oppositely, when the light comes from rarer to denser, then the refractive index will be more than 1. So by that way, we can say that optical density is clearly explained with the help of refractive index. Okay, optical density, it is clearly explained with the help of refractive index. Refraction of light and frequency. So we all know that is a property of the velocity of light that depends on two things, that is v equals to f into lambda, where f is frequency, okay, and lambda it is wavelength. So two things are there. Now the question has come, as the sorry, as the refraction of light, it is totally depends on the velocity of light in different medium. So how does the frequency and the wavelength changes with the refraction of light? So you will be astonished that frequency, it is a sole property of the source from where the light emits. So if we can write, it is frequency, and we have to mention that it depends on the source of light. So one thing you see, when the light ray comes from one medium to another medium, so the source of light, it is same. If a light ray is incident to one medium and goes to another medium, so that is occur due to the speed of light, and here the light ray bends, but for that reason the source, what source you have taken, that source, it is not changed, the source should be same, and frequency of light depends on the source, and that's why due to refraction frequency is not changed. We have told now that velocity is changed when it comes from one medium to another medium, but the frequency is not changed, it should be constant. Then clear that the wavelength of the light is changed when the refraction occurs, that's why the velocity of light is changed. Now we have to see how the refraction, due to the refraction, that the wavelength of a light changes. Okay, so frequency, it is only one property that is not changed due to refraction, but the wavelength is changed. We have come with the same equation, v equals to f lambda. Okay, assume we are taking two medium, it is medium 1 and it is medium 2. Okay, this is the angle of incidence I, that is the angle of refraction r, p, q, r, and it is ab. Okay, now the question has come, what will be the speed of light in medium 1? We are taking, it is v1. So v1 means we can write it, v1 equals to f into lambda 1, where f equals to frequency and lambda 1 equals to wavelength in medium 1, means wavelength of light in medium 1, and here the velocity changes in medium 2, it is v2. So v2 is f into lambda 2. Obviously the frequency will be constant, and lambda 2, that is the wavelength in medium 2, right? So from here, if I want to find the refractive index, then we can able to find how the refraction and wavelength is related with each other, because refraction we denote it by refractive index. So let's see the refractive index here. So refractive index 1 mu 2, that should be mu 2 by mu 1, and just now we have seen that should be v1 by v2. Just now we have seen that velocity of light in medium 1 and velocity of light in medium 2. So here v1 can be represented by f into lambda 1, and here it is represented by f into lambda 2, it is 1 mu 2. See, f will be cancelled out, so here lambda 2 is equals to lambda 1 by 1 mu 2. Okay, so from here we can write lambda dash or lambda 2, it is equals to lambda 1 by 1 mu 2. So if your refractive index is more than 1, then the wavelength will be decreased. That means when a light comes from rarer to denser medium, then the wavelength is decreased, because in that case refractive index is greater than 1. So we can write rarer to denser, wavelength decreases. And when the light ray comes from denser to rarer, so in case of denser to rarer, we have seen just in the previous part, you see, when the light comes denser to rarer, then the refractive index is less than 1. So less than 1 means this lambda 2 will be more than lambda 1. So wavelength increases. Okay, so this conclusion you have to remember, as well as this relation also, how the refractive index is related with the wavelength of light in a medium. Okay, so if the wavelength is given, assume in a medium that wavelength it is given to you, and if I want to find the wavelength in another medium, how we have to do? Let's see. Assume in one medium, assume in vacuum, okay, the wavelength lambda is 6000 angstrom. Okay. So 6000 angstrom means 6000 into 10 to the power minus 10 meter. That is the wavelength. And 10 to the power minus 10 means 6 into 10 to the power 7 meter. In vacuum, we can denote it by lambda v. And the light comes from vacuum to glass. Okay, so you have to find the wavelength of light in glass. Okay, refractive index, it is given to you, that is V mu g, it is given to you 3 by 2, that is 1.5. We have just now seen. Then how you can find lambda g? As the light ray comes from vacuum and it goes to glass, so definitely it should be velocity of light in vacuum, that can be denoted as c, and it is velocity of light in glass, that is Vg. C equals to F into lambda V, and Vg equals to F into lambda g, just like the previous thing. So from the equation we have seen here that we have just now seen, so we can see lambda g, that is equals to lambda v by mu g. So mu g means mu g with respect to v. So lambda g is equals to lambda v with 6 into 10 to the power 7 by 3 by 2. So 3 by 2 means it will come here. So 3 2s are 6. So it will be 4 into 10 to the power 7. So 4 into 10 to the power 7 meter, that will be your wavelength. Now you see, as the light comes from rarer to denser medium, you see the wavelength is decreased. Initially it is 6 into 10 to the power 7, now it is coming 4 into 10 to the power 7. But if the opposite thing is occurred, if the light goes from denser to rarer, then you can see that the wavelength of the light is increased. That is the relation of wavelength with the refraction of light. Okay, factors that affecting the refractive index of a medium. So by the things we have discussed just now, so by that only we can understand it is clearly depends on the optical density of a medium. Okay, so optical density means if the optical density is more in a medium, so in that medium the speed of the light is less, and as the speed of the light is less, the refractive index of light is more there. Okay, so let's see an example. Just now we have seen that the refractive index of glass with respect to vacuum is 1.5. Okay, refractive index of glass with respect to vacuum, it is 1.5, and here the speed of light in glass, that is 2 into 10 to the power 8 meter per second, where in vacuum the refractive index we generally take 1, and the speed of light in vacuum is 3 into 10 to the power 8 meter per second. Okay, so by that, in another way also you see refractive index of water with respect to vacuum, that is 4 by 3, that is around 1.33. Okay, and here the speed of light in water is 2.25 into 10 to the power 8 meter per second. So more the speed, less the refractive index, and in opposite way, more the refractive index in a medium, the speed will be less. Okay, so that is the dependency of refractive index with the optical density of a medium. Coming to the point number 2, that is a very common thing and we all know that is temperature. In the previous part, whenever we have discussed that the refractive index, or you can say the optical density of a medium, it depends on the intermolecular force. If the intermolecular force is more, then the optical density will be more. If the intermolecular force is less, the optical density will be less. So if you increase the temperature, so as the temperature increases, you all know the intermolecular force decreases. So intermolecular force decreases, then optical density increases. Optical density decreases, I'm sorry, optical density decreases, and refractive index, basically this refractive index only shows the optical density numerically. So refractive index, that also decreases. If optical density decreases, then refractive index decreases, and if refractive index decreases, speed of light, this is increases. So that is the relation with temperature and the refractive index. As you increase temperature, then intermolecular force between the molecules of a medium will be decreased, and as it is decreased, the refractive index will also decrease, the optical density will decrease, and the speed of light increases. Okay, that is the another factor. Coming to the next one, and that is very interesting. That is number 3, color of light. Color of light, what is it? We know there are 7 colors. Okay, and when they are combined in together, we'll get white color. When the different colors are moving through a medium, moving through the vacuum, I'm sorry, moving through the vacuum, then their speed is constant in vacuum. Okay, and that speed we all know, that is 3 into 10 to the power 8 meter per second. So here the different colors, that is Vibgyor, all the colors should have same speed, 3 into 10 to the power 8 meter per second in vacuum. But when it travels from one medium to another medium, then the speed is changed. We know that in red, the speed is maximum for red light. Speed is maximum. In opposite way, violet, speed is minimum. So for red light, if I want to find refractive index, assume I have taken two mediums and we are passing red light through it. Okay, so if I passing red light, we have to mention here it is a red light. So here the path will be this. So that is angle of refraction. But here we have to give emphasis on that angle. That is we have done that is deviation, angle of deviation. Okay. So for red light, deviation is minimum. So if deviation is minimum, you just try to understand. Then refraction angle or angle of refraction, that is maximum. Okay. Here we are just finding mu 2 1, that is sine I by sine R, and here sine R is more because the value of R is more as the deviation is minimum. In the another case, you see, if we are taking the same two medium, but in this case we are using violet light. It is violet light. Okay, and here the angle of incidence is I and the angle of deviation delta, it is, you see, that is maximum, because the speed of violet is less, so R is minimum. We all know again that 1 mu 2 equals to sine I by sine R. Comparing these two equations, you see here the sine R is more because here R is more. Here the sine R is less because R is less here. So for that case, red light the speed is maximum, then the refractive index is minimum. Why? Because you see, as speed is more, so deviation is minimum. So as deviation is minimum, angle of refraction is more. So as angle of refraction is more, the refractive index will be less. And for violet light, refractive index is maximum. So by this way, refractive index is related with different color of light. As the color is changed in a medium to another medium, then the refractive index is also changed. Okay, refraction of light through a glass slab. Okay, so it is an experiment. That experiment, if it is possible, I can do it in front of you, but in board it is not possible. If I got a glass slab, then I can show this experiment in front of you. Let's see if I can I can make a video for that. So assume if a light ray incident on one surface of the glass slab and it passes through the another surface, what will be the path? Assume a light ray is incidenting here. Okay, so when the light ray PQ, it is incidenting on the surface AB, so it is rarer medium because we are assuming it is air, and it is a glass slab, so we have to draw a normal here. Okay, and that one is your angle of incidence I. In this case the light will bend towards the normal. Now you see, when the light ray bends once towards the normal, then in this path the light will come in a straight line, because here the total path is what? It is totally glass, so there will be no deviation, and then it incident to another separation of the glass and air, that is DC. If I have drawn a normal here, okay, so from here the light comes from denser to rarer. So as it comes from denser to rarer, it will be deviated by this path. Okay, it will move away from the normal. So if it is angle of incidence I, it is angle of refraction R1, and it is angle of incidence to the another surface. So that one we have taken R2. Why we have taken R2? Because to just make a simple relation between R1 and R2, and that one is known as angle of emergence. That means it is gone outside. So that is the path through a glass slab by a light ray. If the glass slab is not come in front of the light ray, then the light should pass through this path in a straight line. But due to the presence of the glass slab, the light ray comes here. Okay, so if I give the name, it is R, it is S, and here it is now give the name, it is T. So the light ray should go with the path PT, but due to the presence of the glass slab, it goes from PQ to QR and RS. So there you see a separation. The separation between two light rays, where the light ray pretend to be go, but where the light ray actually goes. This is denoted by small l, and it is denoted by lateral displacement. What is lateral displacement? The lateral displacement means it is the length or the separation between two light rays where the light ray pretend to be go and the path through which the light ray actually goes. The difference between these two paths is known as lateral displacement. Now from this, we just want to find the relation between angle of incidence to angle of refraction. Okay, angle of emergence, I'm sorry. Here you see it is air, it is glass, and it is again air. Now if I want to write that at AB surface, refractive index of glass with respect to air, mu g with respect to A, that is denoted by sine I by sine R1. Okay, and it is mu g by mu A, because the light ray comes from air, goes to glass. So refractive index of glass with respect to air we have seen. At DC surface, here you see, if I am talking only about the DC surface, the light ray comes from the glass and it goes to air. It comes from glass and goes to air. So here we have to find out refractive index of air with respect to glass. Why? Because the light is incidenting from glass, so the refractive index should be calculated with respect to glass. From which medium the light ray incidence, the refractive index is calculated with respect to that medium. So it can be denoted as, here this R2 will be angle of incidence in glass medium. So it is sine of R2 by sine of E. So here E, that is angle of emergence, that should be the angle of refraction in air medium, and that your mu A by mu G is very clear. Okay. Now from here we can write that mu G by mu A into mu A by mu G, that should be equals to 1. Okay, so let's write it down. Sine I by sine R1 into sine R2 by sine E, that is equals to 1, because we have done it earlier also. Mu G by mu A into mu A by mu G, it will be cancelled out, and that should be equals to 1. Now coming to R1 and R2, what is that? We know that AB and CD, they are parallel to each other. AB and CD, they are parallel. Clear? Because this is a glass slab. Slab means the opposite sides are parallel. So the normals, if I mention it N1 and N2, so normals on them, N1 is parallel to N2. These two are also parallel, because if AB and CD is parallel, so the normal on them, they are also parallel to each other. So if they are parallel, now you see R1 and R2, this angle R1 and this angle R2, you see these two normals, so these two angles are exactly just making what type of angle here? Just see what type of angle is R1 and R2. These are alternate angles, right? So these are alternate angles. So R1 equals to R2 because they are alternate angles. It's very clear. So as R1 equals to R2, so sine R1 is equals to sine R2. So sine R1 equals to sine R2, we can cancel this out, and it is coming sine I by sine E. So as it is sine I, we have to write here sine I by sine E equals to 1. So sine I equal to sine E, and if I just taken out sine, so angle I equals to angle E. So in the case of refraction through glass slab, the angle of incidence should be equal to angle of emergence. Angle of incidence should be equal to angle of emergence. And from here we can conclude one more thing, that if I and E is equal, then PQ should be parallel to RS. PQ should be parallel to RS. So you have to remember, whenever you will draw this, you have to remember that PQ and RS should be parallel. If you make it parallel, then the angles should also be equal. Okay, multiple images in a thick plane glass plate or mirror. So this topic, you can say it is one of the very important topic that in the exam point of view, because many questions can come from this part. What it tells, let's see first. Okay, assume it is a thick glass plate or a mirror. So glass plate means what is justified, that glass plate means the light ray cannot able to pass through it. Thick mirror, and this is shown the obstacle that the light ray cannot pass beyond it. So if I have given a name, that is A, B, C, D. So light can incident through AB and it can able to reflect, but it cannot able to pass through CD because it is silvered, shining. Now I have to draw a straight line here. Assume I have kept one illuminated object in this place. Okay, and that point we have taken O. The light ray from the point O, it is coming like this. Okay, so when it incidents here, definitely you all know that the light, it is entering from a rarer medium to denser medium, so it will just bend. Okay, it will not go by the straight path, it is just bend towards the normal. And from here, from the surface, as we have learned that partial reflection and refraction, some part of the light should be reflected. Okay, some part of the light should be reflected. And as it is incident here, the another portion. So from here, the total light it should be reflected, and it will come here, total reflection. And as it is incident on this point, assume it is O dash, and this point should be taken O double dash. So as the light ray incident from here to AB, so definitely it is rarer from denser medium, so the light ray will deviate little bit. Okay, but little amount of light, it can be reflected from the first part surface also. It will incident here, okay, and it again got reflected here, okay, and from here it is little bit deviated. So this type of multiple refraction, it will be continued here. Multiple reflection and refraction together, it will continue. If you increase the length, so the light ray will be increased, the reflection will be increased. Now the problem is that as the light doesn't cross the CD portion, then what will happen? Now if we have looked from here, then we will see the light rays coming behind the glass slab. Behind means if we increase the light ray by the dotted line, we will see one point here, because whenever we have to see by our eyes, the light always gone by a straight line, because we cannot see the light in bent path. So this point we have to take, it is A dash. Okay, and here we will see the first image. Coming to the second one. Oh, paints here. In this point, we will see another image of the same object. If I extend this line, we can see another image. The same, if we have taken the another light ray also, we will see multiple images here. Okay, so just like continuous multiple images we have seen in the case of a thick plain glass plate. Now the question has come, out of these images, which image should be brighter? Okay, out of these images, the brightest image will be A2, that is the brightest image. Now what is the reason behind it? The reason is that if I am talking about the first image, so some amount of light should be reflected from the first surface, because first surface is the transparent surface. Here no silvering is given, so most of the light will not reflect here. Very little amount of light will be reflected. So as little amount of light is reflected here, so the intensity A dash should be very less. But if you see for A2, it is reflecting from the silvered surface. Silvered surface, we know, we have seen our glass. If the back surface is silvered, so we know from here most of the light should reflect. So from this point, most of the light should reflected, and here you see from the first surface little amount of light is reflected inside also, but that is also very less, because this surface, that AB surface, it is the barrier of a transparent surface, and the maximum light can pass through it. Maximum amount of light that is coming from O, that is going by this path through the point O double dash. So if we see by this path the point A double 2 or A double dash, here we will get the brightest image, and after that, as it will go on, the intensity of the images will be decreased. The intensity of images will be decreased. So that is the multiple images form in thick glass plate. That diagram you should practice more. This diagram, I'm definitely telling you, it will come any one of your exam. The internal exams, if it is taken, there these questions will definitely come. Okay, now the last part, and though it is not very important, but as it is there in your book, I will just make you do. That is principle of reversibility. What is principle of reversibility for the case of refraction? The principle of reversibility tells us that if a light ray comes from one medium and goes to another medium, and it is rarer and it is denser with an angle of incidence I, then the angle of refraction will be R. Then it is told if the light retraces in same path, means the light ray comes from this medium and goes to here. If the light ray retraces, means if the source comes here and it incident here with an angle of R, then definitely the angle of refraction will be I. Means on which path the light ray goes, if the light ray returns, it also go by same path, and that property is told as principle of reversibility. If I have taken it is medium 1 and it is medium 2, we all know that for the first case, if I have written it in black color, that mu2 with respect to 1, that should be sine I by sine R, because here the incident angle is I and the refracted angle is R. But when we come in reverse order, then angle of incidence is changed. So the refractive index of medium 1 with respect to 2. Why? Because then the light ray comes from medium 2 and it goes to 1. So refractive index will be 1 with respect to 2. Because from which medium the light ray comes, we have to take the refractive index with respect to that medium. So here it will be sine R by sine I, because you see here R is the incident angle and I is the refracting angle. Okay, so if I multiply here 1 mu 2 into 2 mu 1, so sine I by sine R into sine R by sine I, it will be cancelled out. So definitely 1 mu 2 equals to 1 by 2 mu 1. It is another proof by the help of principle of reversibility. Okay, so it is not very much important, but you can see it how the path is retraces by refraction. Okay.